Okej, unë vetëm du të shikoj si është si duket Jo, shiko, unë duhet të konfirmoj që jeni aty, e kupton? Mi më ande nga fundi. Si tha njëri tha profesor, tha, kam 2 javë që s'kam kryer flokët, tha, ç'a më duhet? Okej, shiko, ne po vazhdojmë. Meanwhile, let me get just a small. Ndërkohë ekrani a duket mirë? Whatever we are sharing.
Shumë mirë është profesor.
Okay. Në rregull. Okay, so in what we have started so far, if you remember, last time we talked about the gradient of a scalar. Okay, then we talked about the divergence of a vector. We talked about the divergence of a vector. Then we talked about the divergence theorem. And the fourth one, it was Stoke's theorem. Now, we said that many, when we're dealing with electromagnetic field theory, we have one essential quantity, which is a scalar quantity, being the potential, and this potential is measured in volts. From that one, we are pretty sure, with the knowledge that we have so far, that we can derive a vectorial quantity, which is the electric field. Now, the gradient of a scalar, the way that we wrote it in this way. We denoted it, the gradient, we used a del operator. A del operator is like a delta, or like the delta in the derivative, when we do the derivatives. Then this gives a vector. So the result here, let's write here that we have a vector A. Okay? Let's denote this a vector A. And then we can take the divergence of a vector field, and the divergence of the vector field, we denote it as the del operator times A, okay? And this one, the result is a scalar. So in order to write it as scalar, allow me to write this one as C, which is as a constant. Or that's the best I can come up with for the moment, assuming that it's not a vector quantity. Then we have the divergence theorem. And the divergence theorem, what it tells to us, it converts three-dimensional. So how can I write this one? Probably it's best to write this one dx, dy, dz. This is equal to the, maybe I don't have much space, probably at best write this one as, or, because I'm afraid the volume will be confused for, this is dv, this is equal to the integral over ds. So this is the divergence theorem, and this dv, this is meter cubed, which is the volume integral, and this ds, this is the meter squared. This is the integral over a surface. And the Stoke theorem, it's an integral of ds, which is going to be equal to an integral of dl. Okay? Now, so the first two, I think they are more straightforward. Where the first one is the gradient of a scalar with the divergence vector. And after we talk about this divergence of a vector field, we move into the understanding of the space derivative of vectors, or we call them spatial derivatives. So we have a vector quantity, and we want to see how it changes as a function of some variable. Okay, so there are some sources in sources of fields, which you can consider this as a positive source. It can be like we call it just a source. Actually, a negative source we can consider like a sink, where a field it's absorbed into, or assume that if it's water, it's sinking somewhere. So it's a quantity which has a negative divergence. But now, when we are talking about the space derivatives, we talk about something like this: d over dx. Okay, so we want to check how something is changing as a function of space. But now we can assume that in fields we have two types of sources. One source is that we have a proton or a charge in the middle, and we have electric field extending out, where the flux it goes outwards the same way that a candle lights out. Okay. At the same time, we have another type of sources which is called vortex sources. These vortex sources, what they have in what's special about them is that they are the type of fields which circulates, or the circularity is different from zero. The best, or maybe the most intuitive example is the magnetic field. Like the magnetic field of the Earth, it doesn't have a monopole. It always circulates onto itself. Even the Earth, it has a magnetic field coming out of the South Pole, it comes back in the North Pole, and that's a specific vector quantity which is always present with us. Probably we are most of the time under the we have for millenniums we have been under the effect of the magnetic fields because it's a natural field of the planet Earth, but we have not been under the effect of the electrical fields as much as the magnetic ones. I can correct myself a little bit here, because even when we are under the effect of the electric fields, there is always a magnetic field associated with it if the electric field is not a constant value. Now, we have the lower space of our out in space, at some specific distance. Right now, it's full with satellites which emit a lot of electromagnetic waves, which enables us with using the GPS in our cars, or even when we are walking. If we download the application of maps, that has a connection with GPS, but this is enabled through the intersection of signals from many satellites, which puts a lot of flux of electromagnetic field onto us. But as I said, before the satellite's existence, the human race was at least under the effect of magnetic fields. And this magnetic field, it has a different nature from the electric field, because the electric field, it propagates in straight lines. For the type of source for electric field, you can assume proton, it has electric fields which extend like this. Okay. This is a specific type of the divergence of a specific type of source. But we have also some sources which we call them vortex sources. Now, when we talk about before we go to the divergence theorem, we need to define two types of spatial derivatives. Let me write this one: spatial derivatives, derivatives, and these derivatives we use a del operator. The del operator is this, we already know this one, and we find the divergence of a vector field, and we can also define the curl of a vector field. Okay? So these two are, so the divergence of a vector, we see this one right here. So we did this one last time together. We have not done together, we have not done this, the curl of a vector field. But the idea is that this del operator assumes that this is something like a vector x dot another vector a, okay? And this is also a vector x cross product with a vector a. We know how to calculate cross products. Also in this case, we're just going to write the notation of a del operator into as if it's a notation of a vector, and we are going to calculate the curl of, not the curl, the cross product between two vectors. We know what cross products are. We have calculated the torque, if you remember, using a cross product. Now, one of the components of the vectors which is used in the calculation of the torque or in the calculation of the angular momentum, and just as a reminder, the torque, it used to be equal to R cross force. the angular momentum L, it used to be R cross P. Okay, so here we have two quantities which are found using this this notation. Now, once we have these two components which belong to the spatial derivatives of the vectors, we can insert those into the divergence theorem and the Stoke's theorem. So for the divergence theorem, based also on the name that it has, so here this is the divergence. So we take the divergence of any vector A, we calculate the divergence, and this is a vector, dot product with a vector, so we get a scalar. This is a scalar. So here is just the integral of a scalar quantity over some volume, and this should be equal to the A dot S. And then this goes into here. Now, for the Stoke's theorem, which is the fourth one here, we have that the curl of A, the curl of any vector field A, this is a vector, dot ds, so this is the surface area actually, and this is going to be equal to the line integral of a vector A times dl. So you sit in front, even if you want to memorize, it's easy to memorize the divergence theorem and the Stoke's theorem, because you can interpret the divergence theorem as an integral, as a possibility to simplify an integral over a volume with an integral over a surface area. And the Stoke's theorem is an integral which simplifies a flux integral or a surface area integral. We can substitute it with a simpler expression with a line integral. So in order to do all of these, we need to do a small review of vector calculus, and it's something that you might be the lucky ones, because you'll be the only ones that have a very good knowledge of vector calculus. Not everybody uses it. So in electromagnetic field theory, we do need it, and you do the best to understand the way that waves or that fields behave. The next possible engineers that get a comparable knowledge with you in this area could be the civil engineers that deal with the fluid dynamics, with fluid dynamics. So that's what so these are the four main points that we are going to cover for now. But as you said, before we cover the details of these two, we need to go over some examples of the gradient of the scalar, the divergence of the vector, and we're going to see what is the divergence of the vector field and the current of the vector field. And for the moment, let's see an example. Now, yes, if you have any question, you can just open your microphone.
I wanted to inform you that at 11:30 we have another lesson.
That's a good. Thank you for letting me know this one. And 11:30 you said, right? Okay, good.
Yes.
So let's move fast then. So here we have assume that we have a scalar quantity, which we write here. V is a function of x, y, and z, and what the gradient gives. So I strongly suggest you to go over the definitions in the textbook also. But the gradient, this is defined as the direction and the magnitude of the maximum change of a scalar quantity. So let's assume that you go to a mountain, and you can go at different points of the mountain, okay? And it's a function. Then at each point, if you see the steepest, if you find the steepest point at any point on the mountain, what that is, that can be given by the gradient of a scalar field. So again, you go to the mountain of Dite, it has a function which can be drawn, and which you can plot this one, and you have the contours of the mountain. At any point, the gradient would give the steepest point or the point where you have the highest slope. So if you are given such a function, if somebody is asking, find the maximum, the steepest point in this potential, how can we find it? We just calculate the gradient. So for this one, let's see, for example, what is the steepest point, steepest slope at the point. Let's call this one 236. So in the three-dimensional space, at this specific point, 236, we want to see how this function behaves. The first thing that we need to do is that we have to apply the ax d over dx plus ay d over dy plus az d over dz. Okay, so we want to calculate the space derivatives of all of these quantities. But then here, this operator, we put here the potential, which is a scalar quantity, and this one, we can take this one inside here, and if we do this, this goes away, and this immediately, this is going to be equal to, this is equal in the direction of along the x-axis. We have the derivative with respect to x is equal to y plus ay. The derivative of this one with respect to y, it's x minus 2z plus along the z, we get just minus 2y, right? Minus 2y. And allow me to erase this part. So that's what we get for the gradient of this potential. Now, if we want to evaluate this at this point 236, this is going to be equal to y. This is 3ax plus this is x is 2. 2 minus 12 is minus 10. So this is minus 10 ay. And for the az, we have minus 2y.
Professor, can you move it to the left, the camera?
Sorry?
The camera, can you remove it to the left?
Yes. Yes, it's just it's shifted. Sorry about that. Now, yeah, we're better. Yeah, so this is what we get, and to make it a little clear, we get 3, minus 10, minus 6. These are the components of the gradient of the scalar quantity. Now, what this is telling to us, this is telling that along the maximum change, or not the maximum change, of course it's the maximum change, but it's also the maximum increase of this potential is along this direction. So if we draw here x, y, z, here we have x, y, and z, that means that we are going to have a vector which is 3 units along the x, 10 units along the minus y, okay, so we get something like this, and minus 6 units down into the z. So it looks like at the point which is 236, and 236 is here 2, 3, 6. So we can draw here the point P of interest. It's somewhere here, okay? So if we locate a person right at this point, he or she will see that the maximum increase of this potential is going to be somewhere in this direction, because this is the direction of the gradient, okay? And the gradient is pointing to the to a maximum change, okay? Now, this is the maximum change for sure, but what we can relate to electromagnetic field theory is that the electric field, it can be written as minus the gradient of the potential. And the reason that we need to put here a minus sign is that if the gradient is telling to us the maximum increase of this potential, now we know that if we have a charge here, the electric field is going to point in this direction. And in order to count for the direction of the field, we need this this negative sign. And let's think about just for a moment about this one. So we have a potential around here, which is written as kq over r. Okay, this is the expression of the potential. We calculate the gradient, and the gradient would tell to us the direction along which we have the maximum increase. And the maximum increase, in fact, it's going to be in this direction. So the potential, it will increase pointing this way, but the direction of the electric field, we know that it's going to be outwards, okay? In one sentence, I can say this. If a person is sitting at point A, what is the direction along which we have the maximum increase of the potential? Is this. Then we can have another person at point B. What is the direction along which the potential has a maximum increase again? It's going to be this direction, okay? So, because of the symmetry of how an electric field distributes out or spreads out from the point charge, this would be the maximum increases, right? Even for a point C, we can do the same. But the electric field, we know also that the electric field, it will point out in like this, okay? So we know this much, and that's why we're going to see this one. But probably it was the best time to figure out how we can determine the electric field and the maximum changes. Now, this is how can I say, this potential V at this point, it has this maximum change. But at the same time, we can, so let's say that we have a vector quantity at some direction. Then at the same time, we want to see how much is if the maximum change is along this direction, how much is the change along this axis, along this second pen? What we can do is simple for us. We just can multiply this vector in blue. We can multiply this vector in blue with the cosine of this angle between these two pens, all right? And how can we do this? We just multiply this vector in blue with the unit vector, which is along the vector in black. So this pen is black. That's how we do it. So always we can ask the following. We have a vector A, okay, and then we have a vector B. We can ask the question, what is the projection of A along the B? The projection of A along the B, it can be written as A times a unit vector along the B, okay? And what is the unit vector along the B? This is A times B. B is divided by the magnitude of B, okay? So this is how we can do this. Now, I try to do my best into drawing this figure, okay? But now let's ask this question. What is the change of this potential if along the origin? So this means the following. We are at some point in space, but we want to check what is the slope of this potential if we are looking along the zero, or the point which is 0, 0, 0, the origin of the coordinate system. And to do this one, we need to define this B. What is this vector which is pointing to the origin of the coordinate system? This vector is going to be R is equal to the origin, allow me to write it like this, minus point P. Okay, point P, we can write this one as 2, 3, 6. This is the point P. Just for a moment, okay, you see it. So this is the point P here, and the point 0, or the origin, this is equal to 0, 0, 0. Now, in order to find a vector which goes from point P to the origin, we just subtract these two, okay? So we just subtract it like this, and the answer is going to be 0 minus 2, this is minus 2, minus 3, minus 6. So this vector R, this is going to be equal to minus 2ax, minus 3ay, minus 6az. So this is what the vector R is. And now to find what is so this is the R, but what do we need now? Can I get an answer from you? So if this is the R, what is the next thing that we need to find?
The gene unit vector to vectorita.
That's correct.
Vector,
which points from point P to the... So given this R, we need to find the unit vector along the R, which is going to be equal to the vector r, let me write it like this, divided by the magnitude of r. Okay, and this is equal to, let me erase this part, it doesn't have much essential information. What is the magnitude of r? Magnitude of r is equal to the square root of minus 2 squared plus minus 3 squared plus minus 6 squared. So we use the Pythagorean theorem to find the magnitude of this vector, and we find that 36 plus 9, it's 45. 45 plus 4, we get a 49. The square root of 49, this is 7. And for many times in Albania, 7 times 7, you know what it is, right? It's 42. So we get the magnitude of r is 7. So here the r is going to be 1 over 7 times, we get here a minus 2, minus 3, minus 6. So this is the unit vector r, and what we were interested into figuring out the, Andy, don't be impressed. I wish you don't understand my jokes regarding the, so at this moment, the question is to find how much the magnitude of this vector is along the origin. We are interested into multiplying these two. Okay, so this is what we are really trying to determine. Now, what was the gradient of V? The gradient of V at this specific point, it was 3 AX minus 10 AY minus 6 AZ. We just multiply with these terms, which here we get 1 over 7, that's 1 over the magnitude. We have minus 2 AX, sorry, minus 3 AY, and minus 6 AZ. So we know that here, the 1 over 7, this stands here, and then we have to take, so here we have the multiplication of 3 terms here with another 3 terms here. So in total, we should get 9 terms. But we know that all the non-zero terms, the surviving terms, there will be only the AX here with the AX here, because here we have a dot product. So we have 3AX times minus 2AX, we get here minus 6. Then AY with another AY, we get plus 30. Minus 6AZ, minus 6AZ is plus 36. So overall, we get here 60 over 7. 60 over 7. So apparently, the maximum increase along the origin is 60 over 7. And by the way, what is 60 over 7? We get something like, to get a precise number, 60 over 7. Okay, using a calculator, we get here.
Di ku të 8.50 sa do dalim?
Yes, you are correct, 8.57. So apparently this is the maximum increase of the, let me think this for a moment. Yes, so this is the maximum, the increase along this specific direction. What about, but what was the maximum increase itself? Can we find this? So we need to find, so the steepest direction, it was the magnitude of this number, which is 10 squared, which is 100. Plus 36, 136, plus 9, 145. So what is the square root of 145? 145, we get 12. So it looks like at this point, at some point P, the the highest slope, okay, let's consider the highest slope is like 12. But along the origin, it's something smaller, which drops from something like 12 down to 8.57. Okay, so this is what we interpret with the change or with the slopes. Okay, and of course the units here that we are considering, there will be what would be the unit? Help me in this for this moment. So if this V was volts, this change would be volt per meter. Okay, so this would be the unit of this one. But let me ask you this question: if this was the potential, what would be the electric field? The electric field would be minus 8.57. Okay, because the we told before a moment that the electric field is minus the gradient of the potential. Good. So let's clear this out. Okay, so let's see some. This was the example of a gradient. Then let's move into the divergence. And now the divergence. So first of all, let's do this. What is a dot product? The divergence, we write it like this. And this is let me use this part. This is going to be AX times d over dx plus AY d over dy plus AZ d over dz. And here we take the dot product with AX. Sorry, the AX is the projection of A along the X. It should not be a vector. This is AX times AX. Plus, okay, my next mistake, this is AX. I can clear some part on this side. Plus AZ. Okay, so this is the divergence of this specific vector. And then we know that this is going to be equal to the derivative with respect to x of the AX plus the derivative with respect to y of the AY plus the derivative with respect to z of AZ. Okay. Now, let me ask you a question. So what is the divergence if the vector A is AZ? So what would be the divergence? So if you substitute this A into this equation here, what should be the answer? Can you think about this one for a moment? You can provide your answers if you want to.
Pensiamo sul 0.
Let's check this one. I think it looks to me that you are correct. So let's try to identify first of all how can we write this one? What is the component along the AX? Is 0, right? What is the component along the AY? Is also 0. And what is the component along the AZ? It's 1, okay? It's a constant number 1, which means that if we come here at this divergence expression, we have to take the derivative with respect to x of the 0, which is 0, the derivative with respect to y of the 0, and the derivative of the 1 with respect to z. So this is 0, and the derivative of a constant number is also 0. So if A, you were correct, I think you said 0, Christina, right?
Professor Zero.
Okay, that's yeah, so you were right. So if A is equal to AZ, then the divergence of A, this is equal to 0. What about if A as a vector, this is equal to y, AY? What is the divergence of A?
1.
1, that's correct, because it's going to be 1, because in these derivatives, here we get for the along the x, this is 0, this is y, and this is 0. So the only surviving term here is going to be the derivative of y with respect to y. So this is going to be equal to e over dy of the ay, which is d over dy of y equal to 1. That's correct. So this was the previous one, and then here we get 1. Okay, so this is the divergence. Then we might be interested into looking at the curl of a vector quantities, and let me see if I find yeah. So if this is a vector A, let's try to find the curl of this vector A. So the curl of vector A, we are going to define this one the same way that we have defined the cross product. So here at the top, we put AX, here we have the AY, and here we have the AZ. Here we put a dead operator, because you know that the dead operator, all the components that we can associate to it, they're going to be the following. And the A, in this case, what is the component of A along the x-axis? It's 0. We have no component of this specific vector A along the z, so this is also 0. And the component of y along the y is this one. Then we can try to figure out what we find the component along the ax. Along the ax, we have the derivative of y with respect to 0, the derivative of y with respect to z. This is also 0. So actually this is null, minus ay. So what can we get here? This actually looks obvious that this is also going to be 0, plus az, the derivative of y with respect to x, this is also 0. So apparently, this quantity, this has a curl of 0. So this vector that we see here, it has a curl of 0. But let's assume for a moment, if A was equal to y ax plus x az. Okay, so let's assume that we have so here we are going to change these quantities, and we have along the ax we have y, along the ay we have nothing, 0, along the az we have x. So if this is the case, then let's see what we get here. Along the ax, we have the derivative of x with respect to y, which is 0, because we know that the derivative, and sorry, this is so close to this one that you might be confused. Okay, so this stands like this. So we get a 0 here, minus ay times minus ay, we have dx, derivative of x with respect to x, minus sorry, this is ay, derivative of x with respect to x, and the derivative of y with respect to z. Derivative of y with respect to z, plus az, and this az is going to be the derivative of 0 with respect to x, minus the derivative of y with respect to y, minus the derivative of y with respect to y, okay? So overall, the first term, along the ax, we get 0. So we don't write this at all. For the ay, we get here 1. So we just get here 1 minus ay. And here, we get, this is 0. And the derivative of y with respect to y is also 1. Minus, this is minus az. Okay? So, if the a is expressed like this, we notice that the curl of a is going to be expressed by this expression here. So this is the, how can I say, the curl, which is a spatial derivative of vector quantities, and we need to know this so that we can calculate the Stoke's theorem and the divergence theorem. Now, the divergence of a vector field, I want to remind you just for a moment that in the three orthogonal coordinate systems, including the spherical and the cylindrical, we had some components which we call them H1, H2, and H3, right? Do you remember what these were? So H1, H2, and H3, they corresponded to what?
Metric coefficients.
That's correct. Okay, so they are the coefficients that make possible to construct a meter cube volume element, assuming that some of the coordinates, they are just angles, which are measured in radians. So these are called the metric coefficients. That's correct. H1, H2, and H3. And now I just want to mention something, that the divergence operator, we can write this one as follows. So the divergence operator for all of the coordinate system, including the Cartesian, because the couple of examples that we did so far, we had the Cartesian coordinate system, which is a little more trivial. But let's assume, if we want to write for any coordinate system, we have 1 over H1, H2, and H3. And then here, we can use a notation here, I, J, K. Okay, so the divergence operator for all the three orthogonal coordinate system, it can be expressed in a single expression like here. But now this is an operator, a permutator, which is going to enable, or which offers different permutations of combining I, J, and K. And this is I. And now you have taken programming courses, and I just want to ask your help to write together this expression. So imagine for a moment that this permutation operator IJK, what they are 1, 2, 3. Okay? So I hope you can see this part. This is this operator 1, 2, 3. And this is equal. And by the way, whenever we have the divergence operator, if we write it, how many terms would you expect to see here? you might be expecting to see three terms, right? Because we have the derivative with respect to x, the derivative with respect to y, and with respect to z. So we have x, y, z. We have r, phi, z, or r, theta, phi, right? Depending on which coordinate system you are considering. The spherical, cylindrical, Cartesian. Now here, we see only one term, but the trick here is that in this permutation operator, this means that the ijk, we can change them. Let's assume that ijk, we have here this ijk, this you can consider like this 1, 2, 3. So if 1, 2, 3 is one permutation, the other permutation is going to be 2, 3, 1, okay? And the other one is going to be 3, 2, 1. So this is how, so we just shift this one to the end and that's it. Or you can assume here that we have a combination of r, phi, z. Then we put here phi. Sorry, I have a mistake here. No, this is correct. This is correct. Here we have phi, z, r. So, and I hope, let's try to write the same terms, but having the combinations of I, j, k as 1, 2, 3. So this is something common. This can be H1, H2, and H3. And this permutation operator, we take it out for the moment. We substitute ijk with 1, 2, 3. ijk, 1, 2, 3. And here we have derivative with respect to u1 of H2, H3, A1. Okay? So this is the first term. The next term, so after this one, we make here 2, 3, 1. So this becomes this permutation operator 2, 3, 1. And then we move on and we say here we have the derivative with respect to what is I now is 2. So we have the U2. What is JK? JK is 3, 1. H3, H1, A. A should be I, which is 2. Okay. Then the next permutation is going to be the 3, 1, 2. 3, 1, 2. So here we have 3, 1, 2. And let's write everything down where we work. We have plus the derivative with respect to the third. So here we have I is 3. The HJK, now they stand for 1, 2. So here we have H1, H2. Then the I is 3, A3. Okay, so this is the divergence theorem, or sorry, the divergence of a vector field in all three orthogonal coordinate systems. So you can substitute here for H1, H2, and for all of these, you can substitute here the metric terms that have to be associated with all these coordinate systems, and you can get the correct expression. Now, I want you also to exercise yourselves with this kind of notation, which in principle, this is like you are trying to save time. Also, for example, in Cartesian coordinate system, if you have the divergence of this A, you can simply state that you have the derivative of AI with respect to UI, okay, where I goes from 1 to 3. Instead of writing the same story all over again, so derivative of AX with respect to X, okay, then you say, what am I going to write next? I'm going to say derivative of AY with respect to Y. And then you repeat yourself so much that you wish you could, if you see, we are changing only these terms, right? But you are spending so much time and effort writing down so many terms. So rather than all of these, you can just opt to consider this one, knowing that I is from 1 to 3. The same notation can be used also there. Again, you don't need to memorize this one. You can always write this one on the formula sheet. You don't even write here H1, H2, and H3. You can immediately write them directly the three different expressions. One from the Cartesian coordinate system, write this again for the spherical, and again for the cylindrical. I strongly suggest to write this in the formula sheets whenever you come for the midterm or for the final. Meanwhile, I just want to ask you if you can connect for a moment, including your cameras, okay? Just I want to see you being present. Whoever was at the beginning of the course might know the reason. So I'm not sure whether you're leaving or.
Ja, profesor, se po ja pun, po që jam në krevat akoma, kështu që.
E ka bisiklet.
I know that's a joke, okay.
Ah, zemra sa I bukur që
Ja,
Okay,
më zemra,
okay,
shikon ku jam.
you don't need to express everything, okay? But I don't know actually how. But do you see each other?
Po.
Yes.
Oj, shikoj.
Po.
Or unë se di ku duhet të klikojnë që të shikoj juve. Just.
Hape tek people person.
Të pini.
Te people.
Okay, I see. Jo, është një opcion që është I vogël këtu, dakor, okay. Po unë uroja që të shikoj të gjithë juve në një ekran, po më sa duket I need to scroll down. I shikoni të gjithë shokët e klasës të gjithë në një ekran?
Jo.
Jo, të gjithë, vetëm ato që
Sa
kanë kamerë.
kemi në anë, po.
Okay. Që do thotë të marrë. Okay.
Profesor, ke një opcion që thot change layout, aty mund t'i zgjedhësh. Te ato 3 pikat që janë poshtë.
Okay, faleminderit. Ku e kam këtu po? Po layout që do të bëj tile apo?
Zgjidh atë opsionin që është
Okay.
tile, dhe dalin gjithë.
Po ande, çfarë po ande?
O mek.
Si ka nove ti profesor?
Po mirë që na vjen sekret. Po prap, vetëm 4 persona, 4 studentë kanë hapur kamerën.
Jo, me sa duket 4 është formati këtu se ka më shumë.
Po kjo change layout, unë të kjo change layout. Tile, what can I do here? Okay.
Po provoj një herë këtë parë në profesor se ka më shumë.
E para fare, e para sa e para.
E para është njësoj si që ishte. Nuk është se ka ndryshim.
E para është se po ju e shikoni për shembull të gjithë shokët?
Jo, Klea se shumë. O Filip, pse ke vënë të kaptur?
Okay, so
Kjo
sa duket thjesht u vemi question settings. Let's see the solution. Okay. No, it looks like it's not going to be. Okay.
Është Zoom-i më duket ajo profesor që I shef të gjithë.
Po, kamerën di Stella.
Sa theu Andi?
Ave kamerë.
Si vëron.
Jo, s'po shikoj të Zoom-in. I cannot see this Zoom option.
Jo, Zoom-i është program tjetër profesor. Si shef do të gjithë, tu 5 veta shef maksimumin. Bashkë me veten.
E shikoj, po ke drejt. Atë po arrit shokun, në fakt, uroj të shikoj pak më shumë. Te kjo change layout. What about the spotlight? What does spotlight do?
Spotlight fokuson vetëm një.
E shikoj, është drejt. I just noticed it. We have Marin is back. Okay, we won't fight too hard for this one. Okay, just settings. One final thing. Spasim shumë opsione.
Po profe, po këtë rekordin e ri do ta morim neve, siç morëm atë të kalumin?
Yes, you will, and you'll see yourself exactly like you are right now.
Awesome.
If you go,
Se u ma nga gjysma.
okay, don't blink and drive. Smoking in the lecture is forbidden, Marin, okay? You cannot smoke.
Po, jo, marroj mëzimin, tash jena të bëma bet që për qef neve.
Okay. You really wanted to ruin this excellent moment, Marine, right?
Po sa
Okay.
sa më quo profi, duja 3-4 cigare, patjetër.
Okay, Marine. Okay, so let's jump to another example. But thank you. I just wanted to see how this option of looking the student was.
Po profe,
Probably-
kom dhe pyetje të fundit.
Yes.
Për këto midtermat, si do ta bëjmë nëse mund të tha Europë që do ta bësh më kështu online, po sigur s'është më të besueshme.
Jo, ne do shikojmë fakt. Shpresojmë që pak 2-3 javë brenda muajit prill të përmirësohet situata, nëse mund të
Inshallah.
përmirësohet disi, mund të bëhet në shkollë. Në mënyrë tjetër pastaj mund të jetë kjo që ju të gjithë mund të bëni provimin dhe provimin mund të menaxhohet në forma të ndryshme që mund të jetë mund bëhet sa më kompleks, goxha kompleks, në mënyrë që pyetjet e në rëndëm për shumë student, dhe studentët ndërkohë që janë në provim do kenë mundësinë ose do kërkojmë që të mbajnë kamerën hapur.
Po.
Kjo mund të jetë një version. Kjo mund të jetë versioni i midtermit.
Duket se ishin bëhet ato additional kështu.
Additional është e vërtet, ka filluar këtë javë, sot ka disa additionala, pra nëse ka dikush për ju që bën ka additional, nga lektori i lëndës mund i kërkohet që të mbajë kamerën hapur ndërkohë që provimi vazhdon.
Po, në rregull. Shumë falem.
Atëherë mund ta lëmë te një shembull tjetër. Okay, so doing what we are trying to cover right now will just very soon pass into the Stoke Theorem and Divergence Theorem. And the reason between this Stoke Theorem and Divergence Theorem is that we can derive a lot of relationships or boundary conditions for the vector fields that we care a lot in this course, which is the electrical and magnetic field. But now, before we step, let me see if I can find a different example for you.
Për këto mund bëj një pyetje.
Of course.
Për këtë punën e provimeve, nuk mund ka në një lloj mundësie që ne ta bëjmë si sistemi italian që të japim vetëm në një provim fund për çdo lëndë.
Kjo është diçka që kemi nevojë ta mendojmë pak, por është opsion goxha i diskutueshëm ose i mundshëm. Këto nuk është.
Po si që bë autobioja.
Si?
Mendoj se është më mirë kështu profesor se sa të bëjmë provime online. Vim vetëm fund, besoj se do hapë shkollat deri qershor. Edhe bëjmë sezonin, na një provim për çdo lëndë.
Është me të vërtetë diçka që mund të konsiderohet. Është mundësi, të paktën duhet ta mendojmë pak, ta bluajmë pak, por është goxha e vlerësueshme kur e krahason me provimin online këtë të drejtë. Ndërkohë që shpresojmë që situata të bjerë vazhdimisht në përmirësim dhe shpresojmë asaj rrugë të shkojë.
Ata themi edhe ne profesor.
Profesor, po i vjen që të bësh dhe midtermat dhe finalet në fund.
Po pra një provim.
Jo, mendoj shoku sugjeroi një version që ketë vetëm një provim me shkrim, vetëm finale, jo midtermi në fund.
Okay.
Unë kështu e kuptova.
Po kështu është profesor. Ti jetë vetëm finali në fund. Për shembull sistemin italik kështu e ka, bëjmë vetëm një provim në fund vitit ata, edhe mbyll. Edhe mund ta praktikojmë të semestrin. Qofse varet se do shkojmë atëherë.
Andi të shkon finali bashkë me përqindjen e midtermit, po dole keq atje?
Çfarë do bësh tash Estel? Këto hara.
Si do me i qenë vetëm mos e bëjmë online atë provimizën.
Atë po them unë, veç mos bëjmë provime online kodu.
Okay, so I'll go into one example, but before we jump into the example, I just want to remind all of us why we care for some specific types of integrals. So here, this integral that we see here, which we're going to see it in Stoke's theorem, is a line integral of a vector A with a line dl. So to clarify things, this dl, this has units of meter, this ds has units of meter squared. The first one, it can be called a line integral or a path integral, okay? The second one, it can be called an area integral or flux integral. We call it also a flux because a flux we often calculate it as the number of field lines per unit area. Now let's see an example, which will be the following. Let's assume that we have a vector quantity, and we want to find the line integral. Let's assume this is 1, 1. We want to go from this point to another point here, which is 2, 2. And let's assume that we want to go from this point to this point through this path. Okay. So let's say that the vector that we are going to consider is the following. Let's assume that we have vector A is equal to ax x squared plus ay 3x z squared plus az times minus 2x z. So if we have this vector, what we want to do, we want to calculate the line integral of this vector here across this path. Now, an intuitive equivalence that is worth mentioning here is when we calculate the work, okay, just as let me remind you something. So what is the work equal to? In mechanics, you have seen that the work is equal to force times distance, right? So the force times distance, but this was a dot product. And with this dot product, this meant that if we have an object that we attach it with a force which is equal to 2 Newton, then if we pull this a distance of 2 meters, the work is equal to 2 times 2. In the distance 2, we get 4 joule, right? 4 joule. Then, if the force is 2, but is at an angle, so this is also 2 Newton, the new work is equal to 2, this is the angle theta, 2 times 2 times cosine theta, okay? Then, at the same time, if we have the gravitational force, or which is here, what is the work done by the gravitational force? The work done by the gravitational force is equal to the mass times g, which is the force times 2. What is this in this case? What is if this object is being pulled this way, what is the work done by the gravitational force? Can I have an answer from you? It's going to be 0, okay? Because the angle between the displacement, so this d is the displacement, and the force is 90 degrees, and the cosine of 90 is 0. So this is why the line integral is important. So you might have a force or a field, and calculating the line integral, it can give for us very important quantities. Now, let me ask you, I think, do you remember such a formula where the force is equal to Q V B? Can I get some affirmations or negations regarding this one? Have you seen this formula before? This is the force exerted by a magnetic field on a charge, okay? So if you have a charge in the magnetic field, that's the force, right? And if we have seen this before, we can ask the question, what is the work done by this force on a charge? The work should be equal to force times distance, dot product, okay? And this is equal to force Q V cross B, where B is a magnetic field, B is a velocity, dot D, where D is the distance. So all of these quantities, so if we see here, all of these quantities, they are vectors. Now, this velocity, this is equal to the Q, this is D, the derivative of D, cross B, dot D. Now, the thing is that the velocity and the displacement, they have the same direction, okay? So if an object is moving with a velocity in this direction, that's also the direction of the displacement. But if this is the direction of displacement, if the force is at 90 degrees, you can, if you think this one for less than a minute, you might figure out that this will give a 0, which means that for any charge that is in a magnetic field, the work done by the magnetic field is equal to 0. Okay? Why 0? Because the angle between the force and the displacement is going to be 0. Now, with this equivalency of what we want to find using a line integral, and probably an intuitive equivalency and examples, I just want to erase this, and you can always go back and see how we used to calculate work in different parts of the engineering education. And let's come back to here. So now, for a moment, we have this vector field here, which has different components along the x, y, and z. We want to calculate the line integral along these paths. Now, let's first consider this path here. The most essential thing that we did in the first week in class, it was this. What is dl? dl, this is an expression that you should write in the formula sheet whenever you come for an exam or when you do your homeworks. They are explicitly stated in the textbook, so it should not be difficult for you. So please, just get it from the book. So this dl, this is written as the displacement, any infinitesimal displacement along the x, which is denoted dx along the x, plus any infinitesimal displacement along the y, which is dy times ay, plus dz az. Okay? Now, this is something, let's say, I can say this is the most important thing, okay? There's nothing to memorize, you just write this on the formula sheet and you should be good. So this is dl. Now, you keep this here. If you are going from this point to this point, what is dl? So from here to here. This is x-axis, this is y-axis. So, is the z ever present along this path? So this is a vector. Can I get an answer from you? So what is dy if we're moving along this line? Is the y changing? Understand there epsilonit. Nëse ecën të kjo via horizontale.
Jo.
Jo, shumë e drejtë. Që do thotë d epsilon është 0, po dhe dz është 0. Pra këto të dy termat ikin. E vetëm gjë që na ngel atëherë kur ecim përgjatë këtij segmentit, kemi dx ax. Okay? Kur ecim përgjatë segmentin A, ky është segmenti B, që do gjeni më lart. Pra segmenti A është ky, gjatë segmentit B, dl-ja është vektor ky, është i barabartë me dy her a epsilon. E ka dhe kjo, plus delta x, dx ax. Po dx i tu është 0, nuk të shon. X është konstant, dhe që x është konstant, pra të mendojmë të gjë. Ndërkohë që ecim gjatë këtij segmentit B, x-i më sa është barabartë, x-i është barabartë me konstant, për shumë të konstant. Po dx-i sa është diferenciali i një vlerë konstante do të jetë 0. Në qëtë 0, ne e lëm të, sa të marrë që fshirëse. So we get this. So this is along path A, we get this, along path B, we get this. And then, let's see, so let's keep them here associated together. Çfarë vlerë ka vektori A në qoftë se ecim gjatë segmentit A, segmenti A e vogël. Çfarë vlerë është më kjo A-ja këtu? Let's write it like this. This A, I'm writing here in parentheses along the segment A e vogël. This is equal to ax. What is x if you are moving along this component? It's x, it's changing, right? We keep this one x squared plus ay. Now, 3, what is z? Z along the axis is just equal to 0. This is also 0. So the only term, which is surviving term, is this, okay, for the whole A. And then the component, which is A dot dl, in this case, it's going to be equal to x squared dx, okay? This is just going to be x squared dx. So if we integrate this over this range, let me have a look here. We are going to integrate. This is we integrate from 1 to 2, and this is going to be x cubed over 3, 1 to 2. This is 1/3. 8 minus 1 is equal to 7 over 3. Okay, so this is what we find for this axis. Then we need to determine the same thing for this vector if you are moving along the path B. For this vector A along path B itself, this is going to be equal to, what is x along the path B? X is a fixed quantity, is equal to 2, okay? So this is equal to ax, this x squared, we write here 4, plus ay, x is 2, 3 times 2 is 6, z is 0, so you get 0, plus az, we get here 2xz, z is also 0 again, so I think we'll be left with only 4ax. So allow me to erase this. So along the second path, the ADL, this is equal to, and so what is this equal to? I should get an answer from you here. So this is DL. A, it was 4ax, right? Dot product with DL, which was dy ay. What is this dot product here? We have the dot product of an ax with ay, which provides for us that we get a 0, okay? Which means that the line integral of the given vector going from this point to this point is going to be equal to, so the line integral is going to be equal to line integral over A plus the line integral over B, where the line integral over A, we got 7 over 3 plus 0. Now, this is an example for the line integral. Now, what we want to mention next is that I wanted to go, how many minutes were left? We're like 8 minutes. Okay.
Po profesor, të bëj një pyetje, librin do na e çosh çik?
Say it again.
Librin do na e çosh një çik atë se s'po e gjejmë dot si PDF.
Let me have a look regarding that, but I will. Now here we have the divergence theorem, okay? And let's assume that we have a vector field which is given by, so let A be x squared ax plus xy ay plus yz az. Can you see this expression? A mund ta konfirmoni pak këtë pjesën? A shikoni do ta shkruajnë aty? Okay, thanks. So the first, let's try to do this divergence theorem. Let's try to confirm the divergence theorem for this vector over a unit volume Q. Let this be x, y, z, and let's assume that this is a cube, and we want to confirm this statement. Given this vector A, the first thing we need to determine is the divergence of this vector A. What is the divergence of vector A? I think there is a reflection. A shikoni të reflektimin të vektori A?
Atë se shohim dot profesor.
Aty.
Aty po.
Okay.
Mos luaj fare.
Sure. So, yeah, the divergence theorem, you can see, now, this is the vector, I think you can see this one. What is the divergence of A? Divergence of A, you know what it is. You take the derivative of this component with respect to x, which is 2x, plus the derivative of this component with respect to y, which is another x, agreed, plus the derivative of this term with respect to z, plus y. So this whole thing is 3x plus y, okay? So if this is 3x plus y, what does this term, so divergence theorem, this states that divergence of A dot d volume, this is equal to 3x plus y, integrating this over dx, dy, dz, okay? So what is this integral? Let's try to find this one. And we notice that here we don't have z at all. So this means that we have to integrate here dz from 0 to 1 times the integral of 3x dx dy plus y dx dy. Now, if you integrate these terms, it's going to be a relatively straightforward expression, but we get a 2, okay? So this is what we get from this side of the integral, okay? Then the next part is to be able to find what is this surface area integral. Ju bëj një pyetje. Kemi një kub që ka 6 faqe, okay? Dhe duam të gjejmë fluksin e këtij vektorit në të gjitha 6 faqet. Sa integrale do na duhet ne për të marrë? Do të kemi 6 integrale apo jo? Pra kemi këtë faqen përpara, faqen brapa, faqen lart, faqen poshtë, kemi edhe faqen majtas dhe djathtas apo jo? Pra siç kemi këtë kubin, do gjejmë për shembull. Jemi dakord? Shpresoj që ti në rregull të këtë pjesa. Pra të marrim area on the front. So let's consider the surface area on the front. The surface area on the front, if this is the x-axis, it's located somewhere here. Okay, well, you know where it is. And the one on the front, we have x is equal to 1. So x is fixed. And here, vektori A. Çfarë vlerë ka ky vektori A nëse flasim për të faqen këtu përpara? Çfarë mund të thoni për të? Mund të gjendë një pra, një gjë dim për atë faqen përpara, është që ka x-i njësh. Nëse x është njësh, le ta zëvendësojmë të njëshin gjithandej, dakor? Atëherë, për faqen në fillim, a-ja si vektor është e barabartë me ax, në rregull, x është njësh plus y, a y plus z-ja. Sa është z-ja këtu? Z-ja ndryshon, është plus y z, a z. Jemi dakord? Pra kjo është ky është vektori A. Ndërkohë, ne duhet të përkufizojmë sipërfaqja. Ne, ju si klas, keni marrë linja algebra, kemi marrë bashkë, apo jo? Dhe tek linja algebra, kemi përmend diçka që çdo sipërfaqe përkufizohet nga vektori që është pingur me sipërfaqen. Po apo jo? Po, për që do thotë, nëse kem kam të sipërfaqe që ju e shikoni me këtë këmbë, kjo sipërfaqe përkufizohet nga një vektor që është pingur. Është unike kjo. Edhe kjo këtu, kjo është vektori që përkufizon atë, që do thotë, në këtë DS, vektori që për shembull kjo sipërfaqe që është këtu përballë këtu. Cili është vektori që është pingur me atë?
Z-ja.
Z-ja që do thotë DS-ja është e barabartë me AZ, kjo është drejtimi. DS-ja pra të in the front, se këtu tani po shkruajmë edhe A-n, edhe area in the front, edhe DS-ja. Kjo është AZ, po AZ-i vetë me çfarë është barabartë? Që është mëson 2y dz. Në rregull? Sepse një pjesë e vogël këtu, se x-in e kemi konstant, pra sipërfaqja që është përpara, x-i është konstant, do thotë 2y dz, janë këto metra katror që na duhen neve. Tani, kjo është A-ja, kjo është DS-ja. Çfarë gjë tjetër që duhet të bëjmë ne? Duhet të gjejmë produktin skalar midis këtyre dyjave. Produkti skalar i vetmi term që mbijeton, nuk e di a shikoni të ngjyrën e blu atje. Kjo është AZ, a duket ngjyra blu?
Po.
Në rregull. Kjo është AX, kjo është epsilon. Këto po të shumëzojmë me këto do datë 0. Edhe kjo do datë 0, e vetmja term që nuk do datë 0 është produkti të dyjave. Që do të thotë A herë DS, kjo është e barabartë me këto thjeshtohen në ngjelet yz 2y dz. Okej? Kjo është ADS-ja. Dhe kjo ADS-ja po të integrojmë, neve do na dalë për që shikojmë çka kemi diçka tjetër, këtu kemi të bëjmë me njëshin, AX-in, Jo, më lejoni pak një bëj gabim goxha të madh këtu. Vektori që është pingur këtu është AX, jo AZ. Kjo është AX dhe jo kjo, por kjo do të jetë termi që do mbijetoj. Sepse kjo është boshti X dhe vektori që është pingur me këtë është AX-i. Kjo është gabim, atëherë do ngjelet vetëm 2y dz. Dhe pastaj kur të integrojmë këtë, kemi 2y dz nga 0 te 1, nga 0 tek 1. Kjo është e barabartë me pavarur nga njëra tjetra. Integrali i y-it, i 2y-it është y. Dhe kjo si integral total do na dali 1. Okej? Pra, ashtu siç gjetëm, nëse marrim të sipërfaqen tjetër, të DS-n këtu. Kjo është y baraz me 1. Sa është sipërfaqja këtu? DS-ja është e barabartë me AY, që shumëzon 2x dz. Kjo është on the right side, pra quajmë sipërfaqen që është në krah të djathtë, pinën e tuaj. Dhe nëse është kjo kështu, kjo është DS-ja. A-ja vetë, në këtë poshtë, do të mësojmë çfarë do të thotë vlerë që ka kjo A-ja tek y njëshi dhe do gjejmë këto lloj integralesh sipërfaqësor për 6 sipërfaqe të ndryshme. Dhe ajo që ne urojmë që të gjejmë fund fare është që kjo divergjenca e A-s, kur integruam me gjithë vëllimin të folium, të jetë barabartë me këtë vektorin A me fluksin e vektorit A mbi sipërfaqen. Tani, në orën 10:30 kë kemi leksionin?
Me profesor Julian.
Me profesor Julian. A ka profesor Julian?
Na e ka çu linkun në email.
Po, profesor, është aty te klasi se e pash.
Jo, nëse profesor Julian është lidh, atëherë unë mund t'ju ta lëm me kaq për sot. Por ju do shikoni detyrën e shtëpisë dhe do lexoni gjithë kapitullin e 2 deri në fund. Dakor? Pra do shikoni këtë pjesën e vector Divergence Theorem dhe Stoke Theorem. Për më shumë detaje.
Gjejmë do të lidh librin o profesor.
Librin?
Po.
Dakor, librin do